Okay, let's quickly recall so that we can contextualize what's going on. And then we first got circulation. And we talked about circulation a lot last week. And this is that line integral, the f dot t ds. And essentially this was looking at the scenario in which we've got a curve in space. So here's x, y. And then so we've got some sort of a curve C, and give it an orientation so it traces itself out in this direction. And the idea is we're looking at the contributions. So if I were to look specifically, say right here, and if this is the unit tangent, right? I'm looking at the contributions of how aligned the field is with the curve. And so if I say the force or say the field in this instance was right there, and we would take a look at what that angle is. And then we'd say, okay, so that is some amount of contributing circulation to the overall thing. And then if this happens at every single point along the curve, that's what this integral is representing, circulation. Okay, so that's what we already talked about. And then I alluded to basically the evil twin, which is flux. Okay, and so flux is what we're going to be talking about today. Just as to quickly finish up the previous section before going into the conservative fields. So flux is, instead of being the contributions that our how aligned you are with your curve, you're going to try to be as orthogonal to the curve as possible. So we've got orthogonal contributions f dot n now, and it's normal f dot n ds. And visually speaking, we're looking now at a situation. So we've got a curve in x, y, z space. Let's give this also an orientation, so oriented. And then if I choose some sort of a point, again, or maybe right here, now we're not looking anymore at how aligned we are. The contributions for circulation are alignment. The contributions for flux, it's alignment, but no longer with the unit tangent. It's alignment with the normal vector. Okay, so a normal vector, which is going to be normal to this vector, so that's normal. And then depending on what the field contribution is, so if the field is like that, for example, we're looking at the contribution between the field and the normal instead of now the field with the tangent. So that's going to be the difference between flux and circulation. Circulation, we're interested in contributions with the unit tangent, alignment with the tangent. Now we're looking at alignment with the normal vector. All right, that makes sense. So that's a recap of kind of what we talked about last time. And now we're going to talk about what this n actually is, because we need a way to compute this. So I mean, actually, I could probably fit it. Yeah, no, I can't fit that. Okay, good.
Yep. So n is by definition orthogonal to t, right?
Yes, so n is going to be defined to be the vector that is orthogonal to both the unit tangent vector d and also k, the unit vector k. And I'll draw a picture of that so you can see what's going on. So it's a derivation is basically, here's one picture that we'll go by. Here's x, y, here's z. So say, imagine I'm going to draw a curve that's kind of resting in the xy plane so we can kind of see. So if we've got some sort of a curve C in the plane, the xy plane, and then at some given moment, let's say it's aligned, it's going around like this in this direction, counterclockwise. If at this particular point, I look at what the unit tangent vector is. So in the plane, that unit tangent vector would kind of be going like that. And then I'm also, k is the unit direction for z. So if I is for x and j is for y, k is for z. So the unit k, which is going to come up into the third dimension. Okay? So don't see this as pointing down. You see it's standing upwards. K is standing up because k is with the z. And then if you were to use the right hand rule, I say, okay, I've got my unit tangent and then K is going into that third dimension. So the way that my hand is, just got there to here, my thumb is coming out of the thing. So that's how we get the normal vector to be specifically coming out of the curve like that. We want the normal to be pointing outward, because if I had to use a different normal, like if it was minus K, then we're talking about the inward normal. So right hand rule is going to give T, K, and then N is out. So this is just going to explain, that's a visual explanation for why we define N, the normal vector, to be the cross product between the unit tangent with K. And we can do that because this computes really nicely. So we get I, J, K. Now the components for T are just Tx and Ty. So Tx, Ty, 0, and 0, 0, 1. That's a 3×3 determinant. And so since there's a bunch of zeros, this makes it really easy, right? So if we do the I step, it's Ty and then a 0. So we get just Ty with the I component. Then we're subtracting. If we did J, we got Tx and then 0. So minus Tx with J. And then with K, it's 0 minus 0. So there's going to be no K component. And here, if we recall that the unit tangent vector is r prime of t over the magnitude of r prime of t, then if r is given by x of t and y of t, then this will just be x prime of t, y prime of t over the magnitude r prime of t. So if I use this information and this information together, Ty is the y component of this, Tx is the x component of this. So I'm gonna put that information together here. They come together and they give this. Get N is equal to y prime of t minus, and then x prime of t all over r prime. So why is this in the x component? Well, because Tx is going to be, or rather, this is going to be in the normal Ty. Well, what's Ty? It's going to be the y component of my t. Here's the y component. It's y prime t over this. And then minus Tx. Okay, well, what is the Tx? Well, that's going to be the x component, x prime. And I actually, since we're doing this in 3 dimensions, I'll extend this to 3 dimensions. So we'll just simply do comma 0 because there's nothing over there. But that at least indicates that we're still in 3 dimensions. All right. So the reason we do this is so that we can get an easier formula to work with. So the f dot n. Yes, do you guys remember in class on Friday when we did f dot t ds? We went through that portion of how to convert the TDS essentially into something that we could more easily compute. All of this is the reason why, because we're trying to get rid of NDS. This is how we're going to replace NDS. And so here, now we've got f dot, well, let's take a look. We just figured out what the n is supposed to be. It's going to be this. So it's going to be y prime of t negative x prime of t comma 0. And then all over r prime. So this right here is the n. And then ds, we talked about that, what that's supposed to be in class on Friday, r prime of t dt. So this right here, we've already gone over that particular derivation. So f dot nds, f dot n dx. And again, we see the very convenient cancellation between the r primes. And I did make a mistake here that I should clarify. Once we've gotten this in terms of the dt, instead of putting a c here, this is a to b now, because we're in the parameterized form. So as soon as we get out of arc length, we can talk about the t going from a to b. So sorry about that. And then when you cancel these, you just are left with the integral from a to b of, and then if your field is f and g, then you've got f of t times y prime of t minus g of t times x prime of t. All of that with respect to the. So again, just like how we did with the circulation, we can convert the flux integral into just a single calculate integral by using this substitution. Okay, so you don't have to 100% understand this. I just wanted to make sure that instead of just dropping the formula definition on you, there's at least some sort of visual representation of what's happening. Okay, so it's attached to the same idea, different symbols. It's going to look a little bit different, but overall the idea is the same. So don't dwell on this. I don't want you to dwell on this too much if it's a little bit, if you aren't 100% sure where everything comes from, that's okay. The main reason is I want you to see there is a chain of dominoes that logically falls from a curve to the definition of well, how we're going to define flux. Okay, thumbs up.
And so in that equation, the integral solving for the flux, is that what we're gonna call it? All right.
So in the same way that the circulation is telling you the total amount of contribution. So as you go on the curve, how aligned it is. What's the difference between alignment and f dot n, right? What are we aligned with in flux?
The orthogonal of the
Exactly. So now we're interested in how is the field passing through the curve or out of our curve instead of is it curling around together with the curve? Okay. Aerodynamics, hint, hint. Electricity and magnetism, hint. You have to take optics, vibrations.
What from T the gradient with respect to Y, or is it just? Or Y the T here?
Where the x's and the y's are coming from?
Yeah.
That's coming from the parameterization of C. So C would be parameterized to some R.
Okay.
And then that's coming, yeah. Okay, let's do the definition. So that you have it. We've pretty much already done the work, so the definition is basically a summary of what we've done. Definition.
Oh, yeah.
Let F be a field FG. So this be a continuous vector field on a region R of R2. And then we're going to let C be a curve parameterized by RT is equal to some x of t and y of t. So this will be two dimensions. Start A at t at A and end for t at B, so A to B. Be a smooth oriented curve in R, so the region that does not intersect itself. It's important. That does not intersect itself. Not intersect itself. The flux. So now here we go. We talked about circulation. Now this is what we actually, the definition for flux. The flux of the vector field F across C. I like the word across there because it gives you a visual idea of what's really happening with the field lines across your curve. Is, and then here's that equation. So integral over the curve C, F dot N ds, because we're interested in how aligned we are with the orthogonal components now, is equal to, so in parameterized form with A's and B's and T's, we get F of T, as we found earlier, F of T times Y prime of T minus G of T X prime of T dt. Another way you could express this is just by going across the curve for f dy minus g dx. Where n is equal to t cross k. And then if c goes counterclockwise, so if I have some sort of a curve, this is my c and it's oriented counterclockwise, then the way that we designed that cross product with the n being t cross k is going to mean the normal is going to be outside. So normal is going to be coming to the outside, in other words, coming out of the curve. And so this is what we would consider outward flux. Okay, so this leads to outward flux. So for a little bit of common sense here, if you design this to be an integral for outward flux, that's how we've defined it. But then suppose we do this integral and then we end up with a negative overall result. Okay, that means we've gone outward and negative. So basically, you've just got some amount of the field engine going in. Okay, so we're going to consider such a contribution as positive in the field. This would result in a positive flux contribution. This would result in a what kind? Negative. Right, so outward is positive, inward is going to be considered negative. And when we go across an entire field, this is really across the entire curve, we're looking at the overall net result. Okay, so if the overall net result is 0, well, that means at some point, basically, all of the outward field contributions cancel out with all the inward field contributions. There's some of Maxwell's equations there, equipotential surfaces there, lots of EMAG with regard to flux being 0. So that's an important idea, not just in this class.
So where n is equal to.
Yeah, where the n is equal to.
Okay.
Okay. Okay. All right. Do you need me to do a visual comparison of flux and circulation, or you think we're pretty locked in what's going on?
Pretty good.
Ready?
Yeah.
Okay. There are a few definitions that don't seem like they're that important. And admittedly, I guess for the context of this class, they're not. However, it is math vocabulary that is used in theorems. So it's best to know what those words actually mean. Going forward. Let's take a look here. I'm gonna first present this to you in the visual way, because I think if you see the visual way, then it'll be you'll more readily accept the technical way that I talk about this. So I'm gonna draw a curve. And essentially, if we can draw a curve that starts and ends at the same spot, then we call it closed. So if it starts and ends in the same spot, it's closed. That's just pretty common sense by looking at it. It's also something we call simple. What do I mean by simple? Well, simple is just going to mean that the curve does not intersect itself. So as I trace out this curve, there is never going to be some parameter t, or 2 parameters t, where we end up at the same place twice. So it's not only the closed, but it's a simple curve. Here's an example. Let's see what this is. So if I say just draw a line like this, and this is our C. Okay, and maybe it's going in this direction. Okay, so is this closed? No, because this is definitely not there. Okay, we don't start and end in the same spot, so not closed. But is it simple? Yeah. Does this intersect itself? No, there's no time t, there's no parameter t value where it's suddenly the same value as it was before. So we can still call this simple. So it's a simple curve that's not closed.
We don't say it's open?
We don't, well, we come to topology seminar.
Okay, so there's something else that's.
Yeah. We don't really worry about that terminology in this scope of this class, at least. Okay, so here's one. Okay, so this is the start and end point. So is this closed or not?
Yes.
Okay, it's closed. Is it simple?
No.
No, it's not simple. Why is it not simple?
It intersects.
Yeah, because if you want to really think about it, at this point, there exist two times t, such that when you plug in that two separate values of t into your parameterization, it'll give you the same location. We can't have that because that results in there being an intersection on itself. Okay, so it's not a simple curve. We don't like these when we're talking about our curves and fields. Yeah.
But it's more.
That's a good analogy if you want to think about it that way. And then. Okay, so is that closed?
No.
Right, so we start here, we finish here, that's definitely not closed. And then is this simple? No, because there exists some time t at which we hit the same value, which means there's an intersection, so it's simple. What?
But
Okay.
I get determinology complex.
But that's that.
Let's worry about this is all you need to know for the custom stuff. If this kind of stuff is interesting to you, come to like for real actually. Topology, these are topological properties that we start to get to.
When and where is the topology seminar?
Tuesday noon in the math department conference room.
Where's that?
If you go to the math department, it's basically just the room with like the table and the whiteboard. Yeah.
What time? You said
Noon to 1.
we have to be.
Okay, closed, simple. So maybe it's gonna come as no surprise when we look at a theorem and it says, I want a closed and simple oriented curve C. What that closed and simple means is exactly that. It's gonna be closed and simple. Cool? Okay, so we have a similar thing that goes on with how we talk about region with regard to their connectedness. And it's gonna be connected and simply connected. Am I good to erase these little just okay.
Yep.
Okay. Okay, so now we're gonna look at actual regions. So instead of thinking about the curve now, we're thinking of regions in R2. Or just regions in general. So here is some region R, okay? What I'm gonna do is I'm gonna call this connected. And here's why I'm gonna call it connected. I'm gonna call it connected because all of its insides are connected to each other. Okay, so I can relate essentially, I can connect any 2 points in R with a continuous function, a continuous curve. Okay. So a continuous curve that's contained within R can attach any 2 points. So these were just example points. I could put any points and I could find a continuous curve. So it's connected. It's also something we call simply connected. Okay, what does that mean? Well, simply connected is going to mean that if I take a closed simple curve inside of here, so say like this, closed simple curve, I can basically deform it and contract it to a single point inside of itself without basically exiting the region. So this will just converge right down onto that point. I can deform any curve, a simple closed curve inside of the region into a single point. That would be simply connected. So here's an example of where that doesn't necessarily happen. So your beloved kind of a torus. Okay, so the region R now is going to be here. Is this connected?
Yes.
Yeah, it is connected. It's connected because if I choose 2 points that are inside of it, like here, say, and even up here, I could still find a curve that just puts them together. Okay, so we're still connected on what counts as the region, but are we simply connected? Right? No, we're not. Because if now I have this in dotted line, if that dotted line is a simple curve, a simple closed curve in R, it's impossible for me to contract this down into a single point. Right, because as if you imagine trying to squeeze it down, it's getting stuck over this hole. And so I can't condense it the same way that I was able to just squish this down onto a single point and it still be inside of my region. Even if I try to squish this down, it's gonna be someplace that's not even inside of my region. Okay, so this is not simply connected. And you can probably guess in a theorem, when it talks about simply connectedness, it's simply just requiring that we actually have the field existing everywhere inside of a simply connected region, because something like this is an issue. And then we can actually have simply connectedness without them being connected. So if I could have the region R is both of these little plots, this is not connected. Not connected. And here's why. Here's a point in R. Here's a point in R. Well, oops. You know, I can't get a curve that somehow bridges that gap with staying completely in R the entire time. Okay, so there's a disjunct. It doesn't work. Is it simply connected though? Yeah, because so long as I choose some simple closed curve in R that is contained in R, we can converge it down into a point. We can switch it down, and it works on both sides. And notice that the condition of simply connectedness is that this curve, this closed simple curve, has to be contained in R. So we don't have to run into the issue of there being something that tries to go between, because that just would never happen. Okay, yes, question.
So, and on the page on the right, up right. The, first region R, is that an inner region that you can do?
Oh, it's like a hole.
Or is that a whole?
Yeah, think of this as like a deformed donut.
Oh,
Yeah, yeah. So donuts, next time you go to Dunkin', you could say, ah, yes, allow me to eat my connected, but not simply connected pastry. And then if you go to the deli and you specify, no, I got the simply connected one, not the. And then if you get two, that's good. Well, we can do so. The other case is suppose you had something like this. Okay, is this connected?
No.
No, not connected. And is it simply connected? No, this one is, but this one's not, so not simply connected. All right. Is that good? So, in the textbook, I want you to go back. Oh, yes, question.
So for this top one on the right, we could say that it's simply connected in a portion of the region, but not all of the region. So it's not simply connected.
Sure, yeah. So, like, if I wanted to take a subset and do the dashed line as a subset, sure, the subsets simply connected, but the overall region R is not. Yeah. So what I want you guys to do is go to the page in the textbook where it has talks about these definitions and see the technical notation for how we describe what's really visually intuitive. Because I can just show you that and you pick it up like that. What's a little trickier is doing the work of seeing the definition in the box and realizing that this is what it's talking about. It's not as easy to do, but that's what being a math student is. It's trying to find the simple way of viewing it from a way that is presented in a very not simple or intuitive way. That's what it feels like teaching myself algebraic topology with professor. I spend about 18 hours in a week to realize that I can draw a circle inside of a circle, and that works. Okay.
For the left, bottom left one, are we allowed to not connected and also simply connected?
Oh, I never finished that. Yeah, this is simply connected. Sorry. Thank you. That would have bothered me on the recording if I would have seen. I was like, okay, we got it. We got everything. All right. So, but visually, so if you see these words, you have an idea of what you have a mind picture of what we're really talking about. Suddenly these words actually have a lot of meaning. The higher you go in math, it's basically just more dense language because every single descriptive word suddenly comes with like definitional consequences. All right, we good to erase this. Move on. So not to totally have some whiplash here, but we're gonna now move into the conservative vector field stuff. This is kind of this is the important part of this section. A vector field F is conservative actually, you know what? I'm grateful that I'm recording this lecture because I would have said something political at that point. Okay, there exists a potential function such that F is equal to the gradient. Okay, so remember we talked about gradient fields? A gradient field, guess what? You take a gradient and that's a vector, which you can call a field. And so a conservative vector field is essentially saying if the field that you have right now is the product of just taking the gradient of something, it's conservative. Okay, so don't overcomplicate that. Basically, we've already talked about this. You just didn't realize it. We hadn't named it yet. But when we're doing gradient fields, we were taking potential functions and then creating conservative fields. So every time you take a gradient of some function and then turn that gradient into a field, you've made a conservative vector field. Okay, was that a question? Oh, I haven't explained this one, I don't think. Okay, so this, it's a backwards in. This is that. And the key such that's are this. Such that, such that, such that. Or such that. Set builder constructions, definitional construction, general implication of defining something with respect to another thing. Set theory, construction, general connotation, and restriction of something that you have defined inside of something. General in-text regarding of such that in a logical implication inline, such that abbreviated form of the English. Okay.
Oh, I have to be less than.
Okay. So here's, I want you guys to notice something, because this is something you can piece together for yourself. I'm just going to give you the lead, okay? So I'll show you the idea, the concept behind this idea, but you should be able to replicate this on your own. Because it involves pieces that you're familiar with already. So let's just say our field is F, G, and H, okay? We have a field F, G, and H. And suppose then if we have the gradient of a potential function, gradient by definition, what's going to be the x component? Okay. Yes, so I want you to think of gradient as basically the derivative operator extended to if you have like multiple components. So it's just phi x. Okay, so the x component, you just differentiate with respect to x if it's the x component. Okay.
Yeah.
And so then the y component you differentiate now with. Here we go. And then what's the last one? Okay. I'm surprised that a math company hasn't come along and made a soda pop and called it Phoebe. I'm just saying, we're taking the shark tank, guys. Launch the launch. No, Fiji. You'd have to have a horrible like speech impediment to mess up. Okay. So here's the thing though. If a conservative vector field, so if we're saying that the field F is the gradient of this function, then we liken all of the x components to each other, okay? So that means the x component over here, F, is equal to what?
B of X.
Yeah, bx. And that G is equal to what?
B.
And H is equal to EZ. Okay, so x component with x component, y component with y component, z component with z component. Any graduate textbook would just say, and it is obvious that, and then they would list all of the things that are obvious. And what they mean by obvious is you take some personal prerogative and then poke and play with this. So if I told you, let's compute what these partial derivatives are. So if I took Fy, what's Fy?
That would be 0.
Well, it'd be phi x one, right?
Oh.
So I take phi x and then now I'm differentiating phi x, which is f one, okay? Okay, and then what about gx? What would gx be?
BY.
Yeah, b yx, but guess what? Those are going to be the same, so we can conclude that if we have a conservative vector field, that it'll have this very special property where fy is going to actually be the same thing as gx. Did I say by? No, fy and gx. Okay, but that's not the only pair that's going to have this, right? So as soon as we smell one pattern, it's going to be true for the rest of this. So what about if I do fz? What is fz going to be? Start with f.
BX.
bxz. Okay, and then what is hx gonna be? Okay,
BZX.
yeah, zx. And then guess what? Well, x and z, z and x, their mixed particles are the same, and so we can conclude that fz is equal to hx. Huh. They did like a white Christmas, where they did like a gift swap with their variables. F normally it's like the x is like, here, have my child. Okay. So you guys do this one. GZ is what?
He's PYZ.
Good. BYZ. And what do you think we're gonna relate GZ to?
H.
Good. H1. Because HY is what?
BZY.
And so what do we conclude?
G of Z is equal to H of Y.
So just from this definition, all of this comes. And what was the key? Poking at it. Give yourself a field, give yourself a gradient. See what's going to naturally occur. So there's going to be a test for conservative fields. And the test is literally just going to say, is this true? Is this true? Is this true? And if all three of those are simultaneously true, the only way that can happen is if your f is a px, if your g is a py, and your h is a pz, that is, the field fgh corresponds exactly to the gradient bx py. Okay? Now, the two-dimensional version of this is, you can imagine how easy that's going to be, right? Because you'll just have f and g and phi x and py. So that's an exercise you can do on your own. Make sure, oh, you know what? Since there's technically only one lab for the entire chapter 17, I'm going to executively decide that this is now a problem on the lab. So show, or basically show, give the test for a field being conservative in R2. Okay, you can throw this on either lab 7 or 8, I don't care, but do it. It's gonna look exactly like this, but easier because you only have to deal with 2 components instead of 3. Okay.
Okay.
Here's why I want you to do that on your own. If you can do that on your own, you're locked in for Green's theorem. Green's theorem is basically just one more step after that. Okay, and if you independently think about that on your own, you're going to be almost 100% times better at this topic. Okay, so do it, please, because you're going to see the beauty and the relationship between all of this pre-stuff before the big name theorems, if you do that. There's just kind of a link now between the computational side and the theory side. So, okay. Questions? Are we good? Okay. Now, if we're wondering about this, it might be like, okay, I want to draw the analogy. So when we thought of the gradient as being like the derivative operation, except we're extended now for multiple components. Now that we've related the field to this derivative, it's almost like trying to go backwards from the field back to the potential function is some sort of anti-differentiation process. And so I want you to think about it like that. is that this field, the conservative field is the gradient. In other words, you have to differentiate to get to the field. And then if you're given a field but need to figure out what the potential function is going the reverse direction, well, it's a little bit more complicated. You can't just take one antiderivative path because now you've got three variables you need to account for. Okay, so the example we do at the end of the class is going to outline exactly the procedure for what that looks like. Okay, yeah.
What do you mean going from the gradient to f of theta?
Well, the gradient to f, the gradient is f. So if you start, so before when we did in 17.2, the gradient field, what that was is I said, hey, here's a function, here's a potential function. I want you to take the gradient of that potential function because that'll give you a field, which we now know is called conservative. Now we've got to go the other direction. So what if I give you a field that is conservative? So I'll tell you it's conservative. That means there somewhere out there exists a potential function. But how do we find that? It's going backwards. All right, so you gotta erase this.
Mhm.
Okay. $44. Man, what a tight schedule. Okay. Let's cut to. There is a procedure that Pearson provides. Is it technically comprehensive? Yes. Do I think it's kind of obnoxious? Yes. And for the same reason that some of like in Greek, when you memorize all these noun rules, it's not really rules, it's just a pattern of how it usually works out. So once you do examples, then the procedure is kind of just obvious. So I think instead of just writing down the procedure, if you want to use the procedure, it's in the textbook. But what's going to be more important is this theorem and then doing a problem with the theorem, because then you'll actually see how it interacts with the field. Okay, we talked about, we have the fundamental theorem of calculus in Calc 1. It's like a big result.
Yeah.
This is going to be the first fundamental theorem for vector calculus, basically. So let R be a region and this actually works if we're in R2 or R3, so I'll just put R2 or R3. And let put what? I wouldn't put R then because you introduce there's yeah. There's a lot of pain that can be introduced in just one little chain, but yeah. The technical reason for why that gets complicated come tomorrow in topology. Anyway. Okay, and let be a differentiable potential function. So we still call it a potential function. And just for fun, I hope you're starting to see some application. A potential function, potential energy, results in a field gravity. Okay. Function defined on R. If f is equal to the gradient of the potential function. Okay, so f, every single time you see this, what should equivalently go through your mind is, oh, f's conservative. Okay. If f is a conservative field, and if I said if f was conservative, this should also flash through your mind, the idea of it being gradient. Then we can actually evaluate a line integral in this conservative field f dot t ds, which we showed to be f dot dr, so it might be presented in either way. We can evaluate it, the potential function at the ending point minus potential at an initial point for all. So an upside down capital A means for all. Because doing that versus writing this, much better. I am far too lazy to write out English words in that. Okay. A, B in the region R So notice this is not a double struct R, don't get confused. This is the subset of either R2 or R3, okay? And all piece wise smooth.
Is that supposed to be beta or
B,
beta, right, this week?
same oriented curves C and R from A to B. Going further in math has made me have to practice some of my script handwriting because we run out of the regular letters. So B is like a basic, so I'd say something like A in script A, B in script B. So if you want to become a math major. So I'm just gonna put down here the integral from A to B of f of x dx is equal to the antiderivative evaluated at B. Dot one. Okay. That relationship between f and then its antiderivative that you're plugging into, I want you to invoke when you're thinking about a field that the phi is the essentially antiderivative. Okay? So you could really, if you really want to just emphasize this idea, you have, instead of writing f dot dr, because if f is conservative, that means f is the gradient of that. So I could say that f, right, f dot dr is equal to, and then bb minus ba. Tell me that isn't beautiful. Completely different context, completely different constructions, and it's the same. And so the question is how and why? Well, it's politics.
Really broken policy.
All roads go to, well, and then eventually categories. But you see that, right? I really want you to see B's as analogous. That your function in the integrand is the field, which that field is just the gradient of B. In other words, derivative of something, antiderivative evaluated at. The derivative, the antiderivative, the derivative, the gradient, the antiderivative, the potential function. Me too.
Wait, don't those invert each other though, or counter each other, the derivative equal, so. The integral of the derivative. Would just equal, wouldn't that just equal the function at those parameters?
Review fundamental theorem of calculus.
Okay.
And as you review that, this is going to really solidify itself.
Okay.
By the time we finish chapter 17, we're gonna have 3 fundamental theorems of calculus.
Three.
Yep, one for line integrals, one for the doubles, and one for triples. And it basically closes your study of engineering calculus. Then if you care to join the light side of the force and then learn actual calculus, you can kind of.
And.
Okay, you guys ready for example?
What color is your force like?
I posit you the question, who brought balance to the force?
Yeah.
Start later. I think it's how I still block and I would say the course. The prophecy never changed.
Okay,
Just the fact.
I want you guys to see this. If I write that f is equal to, or if you ever see this, that the field is equal to the gradient of a potential function. This the same thing, this is the same thing as saying path independence. And what does that mean? Well. In the fundamental theorem we just talked about, did we care what that specific path was between A and B? No, the only information we care about is where did it start, where did it finish? Regardless of what path you take, which means an infinite number of paths, so long as you get from A to B. Yes,
So close. So close that it doesn't end in the same. It doesn't end where it started.
so it's not closed.
No, like it's. So like two part of the circle, but like, so they're doing. 2.5 rotations, one? No, like 2.5 rotations, so they go past the circle and do a little bit.
That's why we talked about the closed and simple curves, because those would count as intersections, because you don't want to redo any points. Okay, so path independence. The best way to not get these mixed up is revert back to what you already know about gravity and potential energy. Okay. If I hold. If I hold this eraser at the height of the top of the whiteboard, it's got a certain amount of potential energy.
Yeah.
Why? Because it's in a gravitational field. And that gravitational field is the gradient of the potential, okay?
What if gravity is not real?
So what happens is, from no matter how I take this, so if I drop the eraser and then now it's down, so this was point A, this is point B. It changed how much potential energy it has, okay? So the fundamental theorem says, well, we know intuitively that how much potential it has down here is different from how much it has here. Do we care about the path at which it took? I could take it on a tour, go, ooh, the eraser comes over here, right? And then the eraser comes over, shakes hands with boy. And then eventually comes down to rest here. When we're looking at the overall change of potential energy, okay, nobody cares what path it took. We just say it started here, it ended there. That's all we need to know. So path independence is going to basically be just the more general description of what we intuitively understand about potential energy and gravity. Yes.
So I'm not certain how this translates to the mathematics, but in physics, the reason why that is because potential energy depends on height. And it's a linear function.
Yeah, and we consider height because in physics you have to oversimplify everything.
Right.
And so the idea is you're on the surface of the earth, where technically on the macro scale, okay, no. Okay, so on the macro scale, here's Earth, okay? On the macro scale, this is the gravitational field going like this, right?
Right.
But when you're on the surface of the earth, on the micro scale, here you are standing on the surface of the earth. At a micro level, the field is just going to look like this.
Okay.
Okay, so the difference between being up here and being down here, right? So you're working against the field.
What I was getting at is, number one, the reason why we have path independence for that is just because height is the only thing that's looked at, so X and Y. Is that what you're also accounting for with the path independence and the gradient function that you're looking at? Okay.
Because the way that would be then defined for your specific scenario would account for only depending on distance away from the ground.
And the other thing was that it depends on height linearly. Do we have any sort of functions that depend on the exponential function? So for example, you go twice as high, you increase the potential four times, something like that.
I wouldn't know in terms of the physical application, but it's theoretically possible if you define it here and then take the gradient.
And that would just be one of the options we have.
Yeah.
All right.
Cool. Okay. I'm going to show you and introduce you to a notation that you'll need to know. And this is, you can add this to your fancy math symbol. Ooh, right? So this is basically now you're taking a line integral over a closed simple curve. Okay, by definition, you start and end in the same place, okay? And so we just figured out that by the fundamental theorem, right? F dot dr is going to be, you take the potential at where it ends and subtract the potential from where it started. That's simple and closed. So its starting position and its end position are the same. So if you end up at the same exact spot, you are subtracting a number minus itself. This is always going to be what?
Zero.
this is a massive property about conservative fields, okay? So if F is conservative, then I might as well have just said that. So if you're presented with a problem and you find the conclusion that under the closed integral, you get 0. Well, it's not necessarily, oh yeah, it actually is gonna be, it's gonna be conservative. It can't happen unless it's conservative. Okay, so this is the same exact thing as this, is the same exact thing as this, is the same exact thing as saying it's a conservative vector field. So get used to seeing multiple representations mean exactly the same thing, and I'm going in between them. Okay? Thumbs up? 158. And I did not get to the example yet. Are you okay with that? Okay, democratically, are we okay if we go to like 210?
Yeah.
Okay.
Yes, smiley face.
And then if we don't finish the entire thing, we can always pick it up on Friday. Wait, today's Monday. Okay, we can do it on Monday.
Wait, do you still want to go through till 2:15?
Okay,
Oh,
well, at least get the problem going here. So here's a field. Qxy minus z squared. X squared plus 2z. And then 2y minus 2x z. We're going to know that this field is conservative. Believe it or not, you can actually test for whether or not that's conservative, because that's what we did at the beginning of the lecture. You'll find that Fy is equal to Gx, and that Fz is equal to 8, et cetera, right?
that a 2z, x squared plus 2z?
Yes, I always put a dash in my z. Okay, and then C is a simple curve from A, which is going to be the point 0 minus 3, 1, and then we'll finish at the point B minus 1, 4, 1. I want to use the fundamental theorem for line integrals. So no longer FTC anymore, right? Fundamental theorem of line integrals to evaluate the integral of C f dot dr. Okay. So integral from C f dot dr is going to be the potential function evaluated at B minus the potential function evaluated at A. Well, were we given phi? What were we given instead? Yeah, we were given the gradient of phi. Okay, if this is a conservative field, this being conservative automatically tells us that f is equal to the gradient. Okay. So that's going to give us a list of equations. The x component of the gradient is phi x, which corresponds to the x component of the field, right? Because if I do phi x, then it's going to give me the next thing. And so what is phi x going to be?
2x1 minus z squared.
Yep, 2xy minus. What is phi y going to be?
X squared plus 2z.
Yeah, squared. Z, and then phi z is like what?
2y minus 3.
Good. 2y minus 2z. Okay, so here's how we're going to do this integration problem. It's basically just a massive anti-differentiation riddle. Since all these are polynomials, there's really no distinguishing difference in difficulty, so let's just tell you x. If you were doing a problem where it was like, this is super, super disgusting and horrible, but then y is super easy, then do y first. But in this case, it's all going to be the same, so just start with x. And so phi, the goal here is we're just trying to solve for phi. So phi, if this is phi with respect to x, and that's what we get, if we integrate phi x with respect to x by itself in a normal integral, technically you're getting back to phi, right? So this would be the antiderivative of 2xy minus z squared dx. Treat y and z as if they're just constants. And that's going to give you x squared y, right? Because here x is the variable, so 2x, x squared, and then the y is constant. Minus xz squared. Now, normally at the end of an antiderivative, you say plus c, like a constant. But what variables are considered constant here? Right, so that means there's going to be not just a single constant, it's going to be a constant function that varies with respect to the two variables that were treated as constants. Because all of those y's and z's, if we do the derivative with only x, that would all go to zero, regardless if those are actually functions. That makes sense. The hardest part of doing these is keeping track of what counts as still being like arbitrary. So we don't know what this combination of y and z is. That's okay. We can figure out what it is. We're going to use the other clues. So we've used this up. You'll never double use one of your pieces of information. That's a big help. So as soon as we use px, you're done. Don't worry about this. We're going to worry about these two. And so what we'll do is let's focus on getting the y. So we know that phi is equal to this. And so this is the key strategy. We pretend like this is the answer, because technically it is. We're going to differentiate our answer with respect to y, knowing that it has to look like this, right? And then we can set what we have equal to that. So phi, right? So let's pretend this is our answer for a second. So phi of this, that's just going to be x squared. And then, are there any y's here? So that's going to go to 0. Now here's some function with y's and z. So we're going to have the partial derivative with respect to y of whatever combination of y's and z that is. Right? So whatever this function is, take its partial derivative with respect to y. And then what do we know this is supposed to be equal to? Yeah, this clue right here. X squared plus 2z. Convenience. Alright, so that tells us that cy of y and z is equal to z. Okay, and so now, since this is partial with y, now let's try to get back to what c actually is, right? Then c of y z is the integral of 2z. Is it with respect, what's the differential going to be? Good. Yes, so we end up with 2yz. Now, the arbitrary constant is going to not just be c, but what variable has still been treated like a constant. Okay, so that's all that's going to be left. So I just call this some function with respect to the last variable that's still arbitrary, which is z. So 2yz plus some d, some function of whatever the z's are. Is that so far so good? Because honestly, that's the hardest part. Once that first chain connection, because then the second one's identical logic. Let's take what we have and actually improve our answer. So this right here is cyz. So this cyz ended up being this. So let's put that into there and see what our improved answer is. Okay, so our improved answer is okay. So we've got phi is equal to x squared y minus xz squared plus the cyz, which we just found out of this expression over here. So 2yz plus some function of the z. We don't know what the z's are. Okay, so we used up this clue. What's the only thing we haven't touched? There you go. So let's take our answer, right? Differentiate with respect to whatever's left. So pz is equal to, okay, that's gonna go to 0 because there's no z there. That has a z squared in it, so it's gonna be minus 2xz, and this has a 1z right there, and this is constant, so plus 2y. Right? And then plus, now this is some function with z, so it'll be d prime of z, whatever that first derivative is. I'm differentiating with respect to z. What do we know this is supposed to be equal to? Yeah, the last clue, 2y minus 2x z. Well, lucky stars, right? So d prime of z is equal to 0. The derivative of what kind of function just gives you zero, a constant, exactly. Now, this is genuinely an arbitrary constant, so dz is just some constant, real number. And since we only require finding a valid potential function, let's just choose the easiest possible one and choose that it's 0. Okay, and so if we know that this, we can just choose d of z equals 0 because that's the easiest constant to deal with. We can at long last plug everything in, okay? So it's gonna be phi is equal to the potential function that we've been trying to find. Don't lose sight of this step. This is the step that you want to anchor yourself to. Which I guess we did technically improve. So here's the next improvement right there. Is the x squared y minus x z squared plus 2yz plus 0. Okay, are we done with the problem? No, but is that pretty much the hardest part of the entire problem? Yeah. Because then the fundamental theorem is going to tell you, okay, if you have a conservative field, evaluating your f dot dr over c is the same as we just care about where we ended and then where you started. Well, we have that information. And we have the potential function from which we're supposed to be plugging that into. So the last step is completely distributive. So the last step is going to be saying, okay, well, f is conservative. And because f is conservative, the fundamental theorem for line integrals is telling me that f dot dr is the potential evaluated at b minus the potential evaluated at a. Now, do you see why we did all this time to go backwards? And so since we have this phi, do we have numbers for b? Do we have numbers for a?
Yeah.
Okay. So phi b minus 1, 4, 1. Phi a is 0, minus 3, 1. And let's see. You're plugging these into here. So minus a minus 2, positive 8, 19.
Let's go simple.
Okay. Right on the money, that's 210. Okay, I hope you know what to practice. Practice well. All right, I'll see you on Wednesday.